Hello. This video is a continuation of gas laws. It will include Dalton's law, Graham's law of effusion, and the kinetic molecular theory.
So we've talked about Boyle's law and Charles' law and Gay-Lussac's law and Avogadro's law. We've dealt with the combined gas law and the ideal gas law. So now we're going to talk about what's called Dalton's law. And when we deal with Dalton's law involves mixtures of gases. So we've got a couple of different gases that are mixed together in a container. And when we deal with Dalton's law, it essentially says that if we look at a mixture of gases, each individual gas in that mixture exerts its own pressure. And that individual pressure for each of the gases is called our partial pressure. And if we wanted to talk about the total pressure exerted by the mixture, it's the sum of all the partial pressures. So each gas in the mixture exerts its own individual partial pressure, and the sum of all the partial pressures will give us the total pressure. So this is the equation over here. This is just saying the total pressure equals the sum of, this is the sigma sign for sum of, the sum of the individual pressures. So kind of visually, if we have a gas here and it's exerting a pressure of 300 kilopascals, and we have a second gas here that's exerting a pressure of 600 kilopascals, and we've got a third gas here that's exerting a pressure of 450 kilopascals, and we were to mix all three of these gases together, and we don't change the temperature and we don't change the volume of the container, the total pressure of that mixture is the sum of the partial pressures. Okay, so we could kind of rewrite it and say the total pressure equals the pressure of gas A plus the pressure of gas B plus the pressure of gas C. Now, we could calculate the pressures of each of the gases individually by using the ideal gas law. Okay, pressure would equal nRT over V. So this would be gas A, this would be gas B, and this would be gas C. Now, since the gases are all at the same temperature and they're all in the same container, so their volume is the same, we could kind of pull out Na and NB and NC and kind of rewrite this equation just a little bit and show that the sum of the moles of each of the individual gases times RT divided by V gives us our total pressure. And again, collectively, this is all dealing with what's called Dalton's law of partial pressures, which basically says that if we have a mixture of gases in a container, each gas exerts its own individual partial pressure, and the total pressure of the mixture is the sum of the parts. Now, when we deal with Dalton's law, we're going to talk about what's called a mole fraction. So the symbol for mole fraction is kind of this italicized X in a way. And when we talk about what mole fraction is, it is the moles of the component in the mixture that we're looking at divided by the total number of moles of all of the gases in the mixture. So over here, this is what we would say, this would be the mole fraction of gas A in a mixture would equal the number of moles of A divided by the total number of moles of gas in our container. So let's kind of look at that in a little bit more detail. Okay, the pressure ratio of a particular component in a mixture is the mole fraction of that gas leading to Dalton's law. So the partial pressure of gas A divided by the total pressure would equal the number of moles of A times RT over V divided by gas 1 plus gas 2 or gas 3 divided by, or RT divided by V, that equals our mole fraction, which equals our mole fraction of A. So we can kind of manipulate that a little bit. And here's the equation that relates the mole fraction of A to its partial pressure. So what we would do is we would take the mole fraction for A, multiply it by the total pressure, and that would give us the partial pressure for A. So let's just use like simple numbers in our head. Let's say that the total pressure exerted by a gas was 100 kilopascals. And gas A was 0.5 for the mole fraction, was 50% of the mixture. Well, the partial pressure for A then would be 50 kilopascals. So we're going to take the partial pressure of the gas, multiply it by the total pressure exerted by the gas, and that would give us the partial pressure of our gas. So let's look at a question. It says a mixture of 10 grams of hydrogen and 13 grams of nitrogen in a 4-liter container at 25 degrees Celsius. We want to calculate the partial pressure of the nitrogen gas and the partial pressure of the hydrogen gas if the total pressure is 33.1 atm. Okay, so this is our total pressure. We're going to need to figure out the mole fraction for the hydrogen gas and the mole fraction for the nitrogen gas. And then we're going to be able to figure out the partial pressure for each of the gases. So before we can figure out mole fractions, we're going to have to convert grams of hydrogen to moles and grams of nitrogen to moles. So see if you can do just that part. Convert 10 grams of hydrogen to moles and convert 13 grams of nitrogen to moles. Remember that hydrogen and nitrogen are both diatomic. So hydrogen is H2 and nitrogen is N2. So when you look up hydrogen on the periodic table, it's 2.02 grams per mole. And when you look up nitrogen, it's 28.02 grams per mole. So 10 grams of hydrogen. We're going to use our molar mass for hydrogen to convert from grams to moles. So we've got 4.95 moles of hydrogen. We're going to take the 13.0 grams of nitrogen, and we're going to multiply it by our molar mass for nitrogen, that 28.02. Again, we're canceling out grams and going to moles. So we've got 0.464 moles of nitrogen. So now that we know the moles of hydrogen and the moles of nitrogen, we can figure out our mole fraction. So to calculate the mole fraction of our hydrogen gas, we would take the moles of hydrogen and divide it by the total number of moles of gas in our container. So the moles of hydrogen plus the moles of nitrogen. So the mole fraction of hydrogen in our mixture is 0.914. It means that hydrogen is 91.4% of the gas mixture, but we just leave it as a decimal because we're going to be having to use it in that form anyway later on in the problem. So the mole fraction of hydrogen is 0.914, and there are no units that go along with that. So use this as your model and figure out what the mole fraction of the nitrogen is in our mixture. So we would take the moles of nitrogen and divide it by the total number of moles in our mixture. And that gives us the mole fraction for the nitrogen. Again, it really means 8.57% of that mixture is nitrogen gas, but we're going to leave it in the decimal form, and we call that our mole fraction. Now, one of the things we can do to check our answer is if we were to take the mole fraction of hydrogen and add it to the mole fraction of nitrogen, it's going to equal 1. It's kind of like saying taking the percents, it's going to add up to 100%. So now that we know the mole fraction for hydrogen, we can figure out the partial pressure for hydrogen gas because we have the total pressure of 33.1. So we would take the mole fraction for hydrogen and multiply it by the total pressure exerted by the gas. And that would give us the partial pressure of the hydrogen gas. So using that as a model, see if you can figure out what the partial pressure of the nitrogen gas would be. Okay, so we'll take the mole fraction for the nitrogen, multiply it by the total pressure exerted by the gas mixture, and that gives us the partial pressure of the nitrogen gas. And again, a way that we can check our answer is if the partial pressure of the hydrogen gas is 30.3, and the partial pressure of the nitrogen gas is 2.84, and we were to add the partial pressures of those two gases together, they're always going to equal the total pressure based on Dalton's law. Okay, so here's a way that Dalton's law can be applied. Oftentimes when gases are produced in chemical reactions, they're collected over water or by displacement of water. So here's kind of a visual of that. We've got a flask here, and there's a reaction that's taking place in the flask. A gas is being produced. The gas would go through the glass tubing, and it would be collected over here over water or by displacement. So the gas would bubble up through the water, and it would push the water out of the flask and displace the water in the flask. Okay, the thing that we need to be aware of is that when we collect a gas over water or by displacement, not only is the gas that we produced going to be collected in here, but there's going to be a little bit of water vapor in here. And there's nothing we can do about that. That's just something that happens naturally based on the temperature. So there'll always be a little bit of water vapor in here. And both of the gases are going to be in the same volume, but they're not going to have the same partial pressures. The total pressure exerted by this gas is going to be the sum of the gas that we produced plus the little bit of water vapor that would be collected along with that gas. And we can look up what the water vapor pressure is because it's dependent on temperature. Just look it up on a table. The warmer the temperature, the higher the water vapor pressure would be. The lower the temperature, the lower the water vapor pressure would be. And it's just a value we can look up on a table. So here's an example of one of those water vapor tables. Again, if you notice, the temperature is increasing as we kind of read through this graph. And if we look at the pressures are going up as the temperature goes up. So to incorporate that, we would have a question something like this. Okay, we have potassium chlorate. There's actually a typo in here. This should say KClO3, not KClO2. I just saw that. So this should say KClO3. It's not going to change what we're going to do, but so we've got potassium chlorate decomposing to produce potassium chloride and oxygen gas. So imagine the little illustration we had on the last slide. We produce that oxygen gas, it bubbles through the water, and we collect that gas over water or by displacement. Whenever you see this statement in a question, you have to consider the fact that there's water vapor mixed in with the gas that you collected, and you're going to have to subtract that value out of the total pressure to get the pressure of the gas that you're dealing with in the question. So we want to look at the oxygen gas that was produced. Okay, it's collected over water at 22 degrees Celsius. The total pressure of the gas above the water is 754 torr. The volume of the gas is 0.650 liters. And we want to calculate the mass of potassium chlorate that was originally decomposed. Okay, so there's a couple things that go on in this question. First of all, since we're collecting the oxygen gas by displacement, we're going to have to take water vapor pressure and subtract it from the total pressure. That'll give us the pressure exerted by just the oxygen gas. The next thing, we'll know the pressure of the oxygen gas and the volume and the temperature that the oxygen gas was collected at. So we're going to be able to figure out the moles of oxygen gas that was collected. And then once we figure out the moles of oxygen gas that were collected, we could do a stoichiometry problem to go from moles of oxygen to moles of potassium chlorate. So that's our thought process. Let's look at the problem. First, we're going to want to get just the pressure of the oxygen gas. Remembering that 754 torr that was given to us in the question is the total pressure. We would have to look up the water vapor pressure on a table. Okay, so I did that for you. So we're going to take the total pressure, which was the 754 torr that was given in the question. We're going to subtract the water vapor pressure. This number came off the table, just so we remember that's where it comes from. So the pressure exerted of just the oxygen gas is 734.2 torr. Now, we don't usually work in terms of torr. We work in terms of ATM when we deal with pressures. Most of your problems have been in that way. So to do a quick conversion, there are 760 torr per 1 atmosphere. So the pressure exerted of just the oxygen gas is 0.966 ATM. Okay, so this is our pressure of our oxygen gas. Next step, we're going to do an ideal gas law problem. Here's the pressure of the oxygen gas. We're given the temperature and the volume of that oxygen gas. Calculate the number of moles of oxygen gas that were produced, and then see if you can do your stoichiometry to figure out the grams of potassium chlorate that were originally decomposed. Okay, so you're going to be using PV equals nRT in the first part of your solution there. You want to solve for N. And I know that it's easy to kind of skip the writing units on all the numbers, but you really truly do want to focus on having those units in your problem. So work on doing that as well. So take PV equals nRT, isolate N so you can figure out how many moles of oxygen gas there are. Plug in the numbers for the temperature and the volume and the pressure. Figure out the moles of oxygen gas, and then figure out the moles and then the grams of potassium chlorate. Okay, so using the ideal gas law, I'm getting 0.0259 moles of oxygen gas. Now that you know the moles of oxygen gas, so where is it? Moles of oxygen gas, you can do the ratio based on the balanced equation to get the potassium chlorate. And then I'll tell you that the molar mass for potassium chlorate, just so you don't have to look it up, is 122.55 grams per mole. Okay, convert moles of oxygen to moles of potassium chlorate, and then moles of potassium chlorate to grams of potassium chlorate. And again, the molar mass is 122.55 grams per mole. All right, so let's see how we did. We've got a couple in the chat there. So 0.0259 moles of oxygen. The balanced equation tells us it's 3 moles of oxygen for every 2 moles of potassium chlorate. And then 1 mole of potassium chlorate, I rounded it off, 122.6 grams of potassium chlorate. So 2.12 grams of potassium chlorate would be decomposed in order for us to produce this amount of oxygen and collect it by displacement. So we're going to move on and we're going to talk about diffusion. Okay, so there's lots of different examples of diffusion, but if you were to bake some cookies in your oven, and that smell of baking cookies in your oven, spreads throughout your kitchen and throughout your house. That's what we're talking about when we use the term diffusion. Okay, and the reason for that is those nice smelling cookie particles are randomly colliding with each other and with the air, and they're dispersing into the room. And when we talk about the average distance a molecule travels between collisions, is called our mean free path. And the fewer the particles, the less the collisions, and the increase the mean free path would be. So when we deal with mixtures of gases and diffusion, okay, we've got this little illustration here. So we've got a container here that's filled with hydrogen gas, and we have a container here that's filled with oxygen gas, and there's just a stopcock here that's separating the gases. And if we were to open the stopcock, the hydrogen molecules are going to start to diffuse towards the right, and the oxygen molecules are going to start to diffuse towards the left. And eventually, the molecules are going to be evenly distributed in the two containers. Okay, and it's not because they want to do that or because that's what they desire or anything like that. It's because when you have mixed systems, they're at a lower energy than when they're not mixed together. Now, the particles in reality, the hydrogen particles are moving from left to right, and then they also start moving from right back to left. And the same thing with the oxygen. The oxygen molecules start moving towards the left, but then they begin to move towards the right, and eventually they're evenly distributed. And it has to do with probabilities, and it has to do with what's called entropy, which is something that is discussed in a lot more detail in Chem 2. Now, there's another term which is very similar to diffusion. It sounds almost the same. It's called effusion. And really the only difference is when you talk about diffusion, you're looking at particles in one container that are moving around and evenly distributing themselves in that container. When we talk about effusion, there's a small pinhole here, and the molecules can just move back and forth through that pinhole. And essentially, the molecules are moving one molecule at a time. So they could be moving from the left to the right, they could be moving from the right to the left, and eventually they'd be evenly distributed on both sides of that barrier. And that's what we deal with when we talk about Graham's law. Okay, so he empirically determined that smaller molecules effuse faster than larger molecules. So if we were to look at the rate of effusion, it's proportional to the inverse of the square of the molar masses of the gas. So the larger the mass, the smaller the effusion rate. Or the smaller the mass, the larger the effusion rate. And if we were to look at two gases, we have their relative rates of effusion in our Graham's law equation. And what we want to notice is that they're inverse. So the relative rate of effusion of gas A is in the numerator on the left-hand side, but it's the molar mass is in the denominator on the right-hand side. They're inverse of each other. And when we look at B, the relative rate of effusion of B is in the denominator on the left-hand side, and the molar mass is in the numerator on the right-hand side. The relative rate of effusion of two gases is equal to the square root of their inverse molar masses. The larger or smaller the mass, the larger the effusion rate, And the lighter the mass, the heavier the mass, the slower the effusion rate. So let's look at an example. Okay, we have two gases. We have hydrogen gas and we have uranium hexafluoride. And we want to figure out their relative rates of effusion. So first, if we were to look at the molecules, okay, the molecules of uranium hexafluoride are traveling at a much slower speed than the molecules of hydrogen gas would be. And that makes sense because the hydrogen gas is lighter, so it's going to be effusing at a greater rate. The uranium hexafluoride molecules are heavier. They're going to be effusing at a much smaller rate. So if we wanted to figure out the relative rate of effusion, first, we're always going to make gas A the lighter gas. Okay, you might want to just, I didn't put that in the PowerPoint. You might want to just put that down as a quick note. The lighter gas make gas A. So in this case, hydrogen has a smaller molar mass than uranium hexafluoride. So we'll make hydrogen gas A and we'll make uranium hexafluoride gas B. So the relative rate of effusion of hydrogen to uranium hexafluoride will equal the square root of their inverse molar masses. So uranium hexafluoride's in the denominator here. We're going to put it in the numerator here. And the hydrogen is in the numerator here. We're going to put it in the denominator here. So what numbers do we know? Well, we can use the periodic table and figure out what the molar mass for uranium hexafluoride is. And we can figure out what the molar mass of hydrogen is. And we would plug that into our square root. So we would take the square root of 352.02 divided by 2.016. And when we plug that into the calculator, we get 13.2 for an answer. It's like, well, what does that number really mean? Well, it means that the hydrogen gas molecules will be effusing 13.2 times faster than the uranium hexafluoride. It's a 13.2 to 1 rate of effusion. And again, this will always be a whole number. It won't be a fraction or a decimal number, as long as we identify gas A as the lighter gas. So hydrogen effuses 13.2 times faster than uranium hexafluoride. So let's look at another way these questions can be worded. Okay, we have an unknown gas this time, and its effusion rate is, my thing got in the way here, move out of the way, 83.3 milliliters per second. And carbon dioxide is 102 milliliters per second. We want to calculate the molecular mass or the molar mass of the unknown gas. Okay, well, first of all, the unknown gas is diffusing slower than the carbon dioxide. That means the molar mass of the unknown is going to be greater than the molar mass of the carbon dioxide. So we look at Graham's law. Okay, since the carbon dioxide is the lighter gas, we're going to make carbon dioxide gas 1. And again, the reason we know that it's lighter is because it's diffusing faster. So, did I do that backward? No, I didn't. Okay, so we're going to put gas A on the top. We're going to put our carbon dioxide on the bottom. It'll be equal to the square root of the inverse molar masses. The 44.01 grams per mole, well, it's not in the question. And you're like, well, where did that number come from? It's the carbon dioxide. Okay, so we look up CO2 on the periodic table, and that's where that 44.01 comes from. So algebra-wise, we're going to need to square both sides of the equation. That'll get rid of our square root on the right-hand side. Then we're going to need to multiply both sides by X, the molar mass of A, and divide both sides by 83.3 and multiply both sides by 102. So we're just doing a little bit of algebra in order to solve for X, or the molar mass of A. So we would take 44.01 times 102 squared divided by 83.3 squared, and that gives us 66.0 grams per mole for the unknown gas. Now, what could be added on to this question is, after you figure out the molar mass for the unknown, maybe it would give you a couple of examples, a couple of formulas for what the gas might be. And you could use the periodic table then to figure out the molar masses and match them up to the unknown and identify what the gas is. So when we have two gases, and we're talking about, it doesn't really matter whether it's diffusion or effusion, we're going to use Graham's law, and the relative rate of diffusion, or the relative rate of effusion of the gases, will always equal the square root of the inverse molar masses. Let's look at some postulates. Okay, it's called the kinetic molecular theory postulates. And we just have a picture over here. This is just a container, and it's got some gas particles in it, and the gas particles are moving around. So gases are composed of molecules. Okay, those molecules are in continuous motion, so they're always moving around, and their temperature is directly related to how much they're moving around. They're going to be traveling in a straight line until they collide into other molecules, or they collide into the container. So another part of this postulate is that molecules are so small relative to the container they're in and relative to the distances that they travel, that we essentially say molecules occupy no space, have no volume. That's not totally true, but they're so small that in this postulate, that's what we're going to be stating. Okay, the pressure exerted by a gas in a container results from the particles colliding into the container. So we've got this particle here. Okay, it's moving along here. It collides into the container. It exerts a force per unit area, and then it bounces off that container. Or this particle here collides up against the container. It exerts a force per unit area, and then it bounces off the container. And we're also assuming in the kinetic molecular theory that gas particles don't attract each other, they don't repel each other, and they have only what are called elastic collisions, meaning that there's no energy that's lost when the gas particles collide into each other or when they collide into the container. Now, saying that particles exhibit no volume isn't true. And saying that particles have no interactions with each other isn't true. But when we talk about ideal gases, we're making these two assumptions. And when we deal with the average kinetic energy of the gas molecules, they're proportional to the kinetic energy of the gas, meaning that if the gas is at a low temperature, the particles have low average kinetic energies. And when the gas is at a high temperature, the particles have an average higher kinetic energy. So the average kinetic energy of the particles is directly proportional to the temperature that the gas is being collected at. And what that does is it helps us to explain all of the gas laws that we've talked about. So it's a good review. When we talk about Gay-Lussac's law, that's the relationship between temperature and pressure. And we said that when temperature increases, the pressure exerted by that gas increases. Temperature and pressure are directly proportional. Well, if we wanted to use our kinetic molecular theory, we could explain that. So here we have a gas that's in a constant volume, and we increase the temperature. Well, that means the kinetic energy of the molecules is going up. The molecules are moving faster. And if the molecules are moving faster, they're going to collide into the sides of the container more often. The force per unit area is going to increase and the pressure is going to go up. If we were to look at Boyle's law is the relationship between volume and pressure. And we're going to this time hold temperature constant. So if we had a gas in a container and it was exerting a pressure, and we were to decrease the volume of that gas, we're decreasing the space that the particles occupy, which means that the particles are going to be colliding into the container more often. The force per unit area is going to increase and the pressure is going to go up. So the kinetic molecular theory helps us to explain Boyle's law. And then Avogadro's law was the relationship between how much gas we have in terms of moles and the volume of the gas. So if we had X amount of gas in a container and we measured the volume, and then we added in more gas, the gas would spread out as long as the volume was allowed to increase. And the reason for that is the more particles you have, the more collisions you have, the more those particles are going to tend to spread out. So the kinetic molecular theory helps us to explain all of those basic gas laws that we talked about at the beginning of the unit. So let's look at molecular velocities. Oops, I didn't get all those off of there. Sorry. So if we were to look at a gas, and the gas has, billions of particles in it, not all of the particles of that gas are moving at the same speed. Some of the particles are moving slower. Some of the particles are moving faster. When they collide into each other, there's an exchange of energy between the particles. And we look at those velocities in terms of what's called the Maxwell-Boltzmann distribution. So when we look at this, we've got our molecules here on the y-axis, and we've got the velocity of the molecules on the x-axis. And we're going to notice that the molecules aren't moving at the same speed. Some of the molecules are moving slower. Some of the molecules are moving faster. So this is the distribution of the molecules with respect to their velocities. And VP is the most probable velocity, meaning that most of the molecules in a sample are going to have this velocity here. Very few of them would have a small velocity or a very large velocity. The probability that the gases are going to be moving at a particular velocity, this is the highest probability. Here we have what's called the root mean square speed, or the root mean square velocity. And this is essentially telling us their average velocity. And when we go to calculate the root mean square velocity, it's the root mean square velocity for all of the particles divided by the number of moles of gas. Not an equation you need. The average kinetic energy of a mole of gas can be calculated. So here we have the kinetic energy, average kinetic energy, equals 1/2 mv squared. Okay, this is our root mean square velocity. And the kinetic energy average for the molecules in a sample equals 3/2 RT. Again, the kinetic energy is directly proportional to the temperature. And if we were to combine these two equations together, because they both deal with kinetic energy, we would get the root mean square velocity equals the square root of 3RT divided by the molar mass. Now, this equation is in red because this is an equation you need to know. Okay, the other equations that we just talked about show you where they came from. So the root mean square velocity equals the square root of 3RT over the molar mass. Now, a little thing we need to know is that the molar mass in our root mean square velocity equation is a little different than what the molar mass typically is. We want to use kilograms per mole for our molar mass, where the periodic table tells us grams per mole. So when we use the periodic table to figure out the molar mass, we're going to need to divide by 1,000 to get kilograms per mole to plug into this equation. And that's going to become familiar when we look at an actual problem. So here's a problem we're going to look at. Okay, we want to mathematically confirm that the root mean square velocity for a mole of oxygen molecules at -23 degrees Celsius is 441 meters per second. So let's look at what we have. First of all, the R value that we're going to use is going to be 8.314 joules per mole Kelvin. We looked at this as being an option for our R values way back at the beginning of the unit. We haven't really used it before, but we're going to need to use it now. And the reason for that is because a joule, which is incorporated into our R value, really equals a kilogram meter squared per second squared. And again, we're going to look at that in our whole problem. So the R value we're going to use is 8.314 joules per mole Kelvin, because a joule equals a kilogram meter squared per second squared. So we start out with our root mean square velocity equation. Okay, the square root of 3RT over the molar mass. So what kinds of things do we need? Well, 3, that's a constant. R, we're going to use this 8.314 joules per mole Kelvin. That means our temperature has to be in Kelvin. It was given to us in Celsius. And it tells us we're looking at oxygen gas. So when we look that up on the periodic table, the molar mass for oxygen gas is 32 grams per mole. But we're going to need kilograms per mole because we're going to want to get kilograms to cancel out eventually. So let's plug in what we know. The root mean square velocity will equal the square root of 3 times 8.314 joules per mole Kelvin times 273 minus 23. That gives us 250 Kelvin. And we want it in Kelvin so that the units of Kelvin cancels out. Since it's oxygen, it's 32 grams per mole, but we want it in kilograms per mole. So we're going to divide that value by 1,000. Okay, this is an important thing. You might want to put a little star next to it because it's very unusual for us to use molar masses in terms of kilograms per mole. And I'm going to show you why that's important in a second. So we'll take 3 times 8.314 times 250 divided by 0.032, and we get 441. You're like, okay, well, that's the number we were trying to find. But where do the meters per second come from? The units are square root of joules per kilogram. So let's look at the units for a second. Moles cancel out. Kelvin cancels out. A joule is really kilogram meters squared per second squared. Okay, now we've got kilograms here and we've got kilograms here. So the kilograms cancel out. So what we actually end up with is the square root of meters squared per second squared. And the square root of meters squared per second squared equals meters per second. So we've shown mathematically that the root mean square velocity of oxygen at negative 23 degrees Celsius is in fact 441 meters per second. Okay, well, what does that mean? It means that the average molecule is going 441 meters per second. Some of the molecules are going faster than that, and some of the molecules are going slower than that, but that's the root mean square velocity of the oxygen molecules at negative 23. Now, think about this for a second. If the temperature were to go up, okay, the temperature's here, that would cause the root mean square velocity to go up. That makes sense. If the temperature goes up, the molecules are moving faster. Okay, if the oxygen was at a lower temperature, T would be lower in our equation, and the root mean square velocity would be less. And again, that makes sense because the lower the temperature, the lower the average kinetic energy, the lower the velocity of the molecules. So let's take a look at this. Okay, here's another graph. We've got nitrogen gas and the fraction of molecules that have a particular speed at different temperatures. So this curve here is the distribution of the molecules of nitrogen gas at 100 Kelvin. If we increase the temperature to 200 Kelvin, the distribution changes itself just a little bit. The molecules have their speed kind of spread out a little bit more. If we look at nitrogen gas at 1000 Kelvin, this would be our distribution. So if the temperature of the gas increases, the average kinetic energy increases, more of the molecules have a higher speed and fewer of the molecules have a lower speed. And the distribution gets spread out more towards the right. And then if we were to look at this graph here, a little bit different. Okay, this time, all of the gases are at the same temperature, but we're varying what the gases are. And if we were to look at that, okay, we've got xenon gas here versus helium gas here. The molecular velocity is directly related to the molar mass. Okay, so since xenon has a much higher molar mass than helium does, the molecules have a much smaller distribution. The molecules are going to be moving more the same speed. As opposed to the helium, we're going to have a much larger distribution. So lighter molecules move faster on average than heavier molecules do, is essentially what this graph here is demonstrating.